Hello everyone. Thanks for joining me on this talk on building serverless Python applications using AWS Chalice. In this talk, we will be basically discussing a bit about serverless computing, AWS Lambda, and AWS Chalice, which happens to be the Python serverless framework on AWS. This would be a short talk where I would be explaining about serverless and AWS Lambda right from the scratch. I will also explain about how you can develop and deploy a simple application using AWS Chalice on AWS resources. Here is a simple introduction about myself. My name is Harsh, and I'm currently working as an intern at Red Hat and a developer outreach at DeepSource. I have been working on Python for the past 2 years, where I have been exposed to a wide variety of Python frameworks like Flask, Django, FastAPI, and machine learning libraries like TensorFlow and Scikit-learn. I also love everything about cloud and serverless, and this opportunity allows me to impart my knowledge about this very subject. With this determination, let's get started up. Let's check out the agenda for today's session. It's going to be short and sweet, I promise. In today's talk, we will be basically knowing the basics of serverless first and how you can get started with serverless development using AWS. You will also get a head start on developing serverless applications with Chalice and why it is such a great choice of developing serverless Python applications. I will also demonstrate a live demo about creating an all new Chalice application, testing it locally, and deploying it on AWS with a short and sweet demonstration. With this determination, let's get started up. Let's bring our attention to the first question. What is serverless? Let us please start with the elephant in the room. Serverless doesn't mean no servers. It simply means that the underlying servers are being hidden from the developer. Like when you are talking with an external API, the underlying infrastructure is completely hidden from you, and you don't have to worry about it. It is a rather confusing term, but don't let it fool you. You will still have to manage some kind of infrastructure. In layman terms, serverless architecture or serverless computing means that your backend logic will run on some third party vendor server infrastructure, which you don't have to worry about. It doesn't mean that there is no server to run your backend logic, rather, you do not need to maintain it. So, why should you bother about it after all? With a serverless platform, a programmer can write code and directly run it on the cloud without worrying about hardware, operating systems, or servers. They can write the business logic as code and then run the code without needing to be aware of the deployment complexities. Applications can get high availability and auto scalability without any additional support from the developer. This can significantly reduce development time and the consequent costs. All of these make serverless a lucrative choice to get started with the development. Earlier, if we wanted to set up our website for global use, we needed to have a server up and running that can process requests and render the application on the user side, isn't it? This was a traditional approach that we followed few years back. Server computing was the de facto way of serving applications, and we needed dedicated engineers to maintain the servers and the backend code. With the introduction of serverless, that requirement has been completely rooted out. I hope you have now understood the basic philosophy and the requirements behind serverless computing. It is universal, and various cloud service providers are offering serverless compute services that we can capitalize on. AWS Lambda is one such service provided by Amazon Web Services. So, what is Lambda after all? AWS Lambda is a service provided by Amazon. In a simpler way, you have to store your function on the cloud and trigger stored functions with events like API calls, database modifications, and many more. Behind the scene, Amazon manages running servers, handling function execution, and allocating resources to successfully complete the execution of the particular function. Sounds easy and fascinating, right? AWS Lambda takes care of needed resources and continuous scaling as a server to successfully run functions. This overcomes the headache of scaling applications, and also we can allow or prevent the function from accessing resources. One of the biggest strengths of AWS Lambda function is the reduced cost of execution. You don't pay anything when your code isn't running. This ensures that you don't pay for the time when you're not actually running the code or your application is not being used. Lambda has more advantages than what I have stated here. So feel free to explore more about Lambda and do let me know if you have any questions about the same. So here is the protagonist of this talk, AWS Chalice. We talked a lot about serverless, Lambdas and all, but where does Chalice comes in? As a developer, the advantages that comes with AWS Lambda are huge. We do have servers up and running, but we don't need to provision and maintain them. Our duty solely relies on providing the function to the servers with an added advantage of paying only for the compute time that we used. Under the hood, AWS Lambda makes use of a whole lot of services to make this happen. And with flexible scaling and high availability, it can be the go-to service for serverless deployment. AWS Chalice is a micro web framework that is very similar to Flask that allows for development and deployment of API-based microservices pretty easy compared to anything else. Except for the code part, the scaling, packaging, and the deployment are all done for us almost instantaneously. You might have made use of a micro web framework like Flask to develop and deploy APIs. Chalice is a very similar web framework with a lot of features and syntax quite similar to that of Flask, albeit it runs completely on AWS resources and offers a single click deployment. The best part about working with Chalice is that we get all the functionality that we can expect from an API development framework, and it provides integrated functionality with most of the AWS toolings like S3 storage, simple queue services, API gateways, and more. Let us see how we can set up a simple project on Chalice. I have already created a folder up here that will serve as the purpose of setting up a Chalice application. So let's see how we can actually make use of it. So I have set up a virtual environment, which you can possibly do as well. Chalice comes with a handy command line interface tool, which can be installed by pip, that allows us to set a Chalice project automatically, test it, and deploy it as well. With Chalice, we can only focus on writing the code that matters, while leaving the deployment and management part to the AWS resources to take care of. To set a Chalice project, we need to configure our AWS CLI, which will provide us with the interface to communicate with AWS resources that we are trying to work on. So first install the AWS CLI and use this command AWS configure to basically configure all those details that you might possibly need to authenticate with your AWS console. Once you have configured the AWS CLI, we can simply move ahead and create a Chalice project. Before we do that, let us first install Chalice by using pip. With a virtual environment in place, we can isolate third-party packages from the main installation and prevent conflicting versions of packaging. So you can simply give pip install Chalice and the installation process will simply go ahead. Once the package has been installed, we are now all set to use the Chalice CLI to set up our new project with ease. Let us see how we can do that once our CLI has been installed. So now you can use this command chalice new project to basically set up a new project that we can possibly use for our purpose. Let us name it BellPie Chalice app. So now we can go into our BellPie Chalice app, and as you can see, we have got an app.py and a requirements.txt. If we just go back to our folder, we can also see some more things. So we have got requirements.txt, which is completely empty right now because Chalice is not a part of the runtime environment. We have also got the .chalice directory, which consists of our configuration. And finally, we have got the app.py, which we can simply take a look right here. So here is our app.py, and this is the entire code that has been implemented in Chalice. If you have worked with Fast API or Flask before, this code might look quite similar to them. It has got only one route that would assign the URL of the application to the function quite easily. The decorators here simply wrap the functions here, which make it easy to write the code logic by breaking them down into separate routes. For now, our application is simply serving only a JSON message, which is a hello world. There are a few more examples that you can possibly take a look at. And we will take a look at how we can implement another route once we start testing it locally and deploy it. So let's move ahead. Now that we have a Chalice project up and ready, let us move next and test and deploy it as well. That will be very simple, I promise. So let us open our app.py file and take a look at the code that we are working on. So here is our app.py file, and now that we already have a Hello World API pre-configured in our Chalice project, let's move ahead and run it locally. We can do that by pushing a very simple command, which is Chalice local. This will kickstart the local development server, and we can just use this particular URL and curl it to see that our JSON message is actually being returned. Sounds cool? So that now that we have got our own Chalice development server up and running on a default local port 8000, and now we can simply go ahead and we can deploy this API on the AWS resources. So we will use the command called chalice deploy, and this command will simply invoke the creation of a Lambda function that would be accessible via REST API endpoint. And let us press it. Okay, I guess I missed out something. Yes, so it is starting to create the deployment package, the IAM role, the Lambda function, and we will get access to a REST API that we can possibly hit at a particular endpoint to start accessing the service that it is providing. And yeah, our application is deployed now and it works perfectly fine. It should work perfectly fine. We can experiment with this. So let us check this REST API URL and send it a curl request to see if it is actually working. And yes, it is working completely fine right now. So our application is now deployed. It is working fine. And we can simply experiment with this by simply adding more routes to the application or making use of some external APIs by GitHub or Twilio to see how we can perform a variety of operations on Chalice and redeploy the same. As a fun exercise, let's make another route right now. This route will simply send a JSON response for the current date time. Let's do it. We can simply remove all this boilerplate code because we simply don't need it, because Chalice is responsible for working around it by default. So let's keep it at API route, mention the date time. Let's mention the date. It should be a very simple function, date, and let's import the date time. And it would return a very simple message. It would consist of the current date time that we will simply make use of it through this datetime module. So let us use return, and the message would be date time, and we will call the UTC now. And yeah, we are done with the code. Let us go ahead and test it if it is working fine or not. It's restarting the local dev server. Let me check on another instance on how it is working. And yes, our JSON message is being returned right now. So now that we feel that this local development server is all fine, we can simply use this command chalice deploy, which will redeploy the entire application to the AWS resources that we are possibly looking at. And this would be simply accessible via a simple get endpoint. It is updating the REST API, and now our Lambda ARN and the REST API URL is simply accessible to us. Let us simply curl it and see if it is working fine or not. Okay, it is missing the authentication token. Let me see if it is working again. Yes, it is working fine right now. And it is showing the message and it is showing the current date time as according to what we were currently looking at. With this, we come to the end of this talk. Thank you everyone for joining me on this short talk on Chalice. I will definitely looking forward to things that you can possibly create with AWS Chalice. If you would like to connect with me further, you can reach out to me on Twitter, LinkedIn, and GitHub. Thank you everyone for joining and see you all. Bye.
A very good morning to all of you. Today we're going to talk about building self-driving cars and what all goes behind into building that. I'm Gagandeep Prihal, CEO and CTO at Minus Zero, where we are building level 5 autonomy for electric vehicles in India. So why building self-driving cars in India is a really challenging task. India has the most unstructured and stochastic driving environment. Anything can happen on Indian roads, and you can't rely on the fact that people will follow rules, right? So, before we dive deeper into this topic, let's try to understand what all goes behind into a driving. First, obviously, is steering left or right, right? Then comes braking, accelerating, that is longitudinal control, object detection and driver's response to that, planning where to go, which path to take, which is the shortest path, etc., and miscellaneous. That can be anything that you might encounter on Indian roads like accidents, etc. When we talk about levels of driving automation, we have 5 levels. First 3 levels basically are used in driver assistance systems where longitudinal and lateral control can be managed by a computer, like changing lanes or maintaining speed, but still human supervision is required. And currently the industry is trying to achieve level 4 and level 5 automation where we all the difficult maneuvers can be done only by computational algorithms with negligible or zero human supervision. What are the different challenges to perception? Number one, obviously, your algorithm has to be robust in detection and segmentation. There can be sensor uncertainty, your sensor might fail. Then comes reflection, lens flare, and even the harsh weather like fog or rain, etc., which can disrupt the functioning of a self-driving car. So all these things have to be taken into account. So let's begin how a self-driving car software controls a car. There are 2 types of planning. Number one is reactive planning, where you react to a certain stimulus. Let's say there is a car in front of you and you react to that, whether you want your own car to brake or slow its speed, etc. Then comes predictive planning. You try to predict the path or future behavior of a certain stimulus. Let's say there is a car in front of you and you have to predict whether the car will turn left or right or it will stop based on various factors, like let's say the car gives an indicator, etc. So the software architecture that is used for self-driving car basically has six major points. Number one, receiving inputs from the sensors, getting perceiving the environment around it from cameras and lidars, creating a virtual map of localization of a vehicle, planning the path, and finally sending it to controllers, which will send it to actuators to actually drive the car. What are environment maps? They are basically which tell what is the state of vehicle in the environment. They can come from various sources like lidars, right? These are the lidar maps. They can come from uh, apps like Google Maps, etc. Or you can use grid maps, where from an aerial view of a vehicle, each pixel is assigned whether it is can be used as a driving surface or not. Various sensors we use for self-driving cars include cameras, lidars, radars, ultrasonics, GNS, GPS, IMUs, and wheel odometry. These are very vital to the functioning of a self-driving car. So then comes computational hardware. Every algorithm that you use to control uses some computational expense. Comes with some computational expense. It uses certain petaflops of floating point operations, etc., which uses power. And the one thing that one needs to realize is that one has very limited quantity of power on a self-driving car, which is not only needed to drive the car and power the systems, but also in doing all the other parts that the car has to use, like a radio or the headlights, etc. So all your algorithms should be computationally inexpensive, which in turn will use very less energy. There are various types of hardware that we used currently in self-driving cars, which includes NVIDIA Drive, PGX Pegasus, or Mobileye, etc. So basically, how we model a vehicle is similar to what you have studied in class 11th mechanics. You coordinate frames, you lump dynamic elements, you create a free body diagram, and using all those dynamic equations, you try to do all the modifications you want to do the vehicle, like speed change, etc. Right? So before diving deeply into the Python-based machine learning part of self-driving car, let's try to understand a bit of what robotics goes behind it. First comes what we use is feed forward and feedback control mechanisms. What is that? From the outputs that you receive from the sensors, you create a prediction. Then there are feedback mechanisms which optimize it whether our prediction is right or wrong. And finally, after optimization, it sends it to the output channels to actually actuate the vehicles. There are various control mechanisms we use, and many of you might have encountered it if you have studied robotics, including lead lag controller, PID controller, proportional interrogative derivative controllers, pure pursuit, Stanley controllers. Do try to look about it on internet if you want to study more. Right? Then comes GPS system to localize the state of vehicle, and inertial measurement units, which is a combination of three gyroscopes and accelerometers, which predict the rate of motion of a vehicle. You can find these sensors even in your daily life, which you use, like let's say in your mobile phones. You turn your mobile and the screen rotates itself. That is basically work that is done by IMUs, right? Then comes LiDAR sensors. Basically, they are similar to radars, but instead of sending sound, they send light. And using the light, they create a point cloud of the shape of an object in the environment. And currently, these are one of the most expensive part in the sensor ecosystem of a self-driving car. And this is what the industry is trying to achieve, to increase the dependency on camera than LiDAR to decrease the cost of a car, right? This is how a LiDAR sensor creates a map of the environment. See, it can detect a car, it can detect the buildings, it can detect the vegetation around the vehicle, etc. Right? Then comes sensor calibration. That is very important because you have to take into account all the latency of the sensors and making sure they all the output from them come at the same time so that computer can make a valid decision. Because let's say uh, there's a car in front of you and you get to know about it after 2 seconds, anything can happen in those 2 seconds. So that thing has to be taken into account. All the sensors have to be calibrated properly. And using multiple sensors is also very essential, because what if one sensor fails in between? Will the car be safe enough to drive itself with the remaining sensors to a safe place or not? Right? Then comes the machine learning part. First, it comes visual odometry, that is used in every machine learning algorithm that we use, including object detection, segmentation, etc. What you have two images at point I and at point I plus 1, at time I and time I plus 1, and you extract and match the features. Okay, this is the car in the first image and this is the same car in image after 1 second, and it has moved a little. After matching those features, you estimation the motion between those two same objects in two images, and using that you after optimizing you can know the state of vehicle, let's say speed of a vehicle in front of you, or even the state of your own vehicle. There are various feature detection algorithms we use, like Harris corners, Harris Laplace, fast corners, which you might have encountered in open libraries like OpenCV, etc. for computer vision. What they do is that the place where there is an abrupt change in the pixel value, there are chances that it is a boundary of a new object. Let's say on a black road there is a white car, so the very place where the level of the pixel, that is the color intensity, changes, that is from black to white, then it is a high surety that it is a boundary of a new object, in which in this case is of car. And this is what all that powers a neural network. So basically we use four major neural nets while driving autonomous car, or even if you have to create an autonomous robotics. Number one is object classification, which will give label to object. Okay, this thing is a car, this thing is a man, this thing is a sidewalk, etc. Then comes object detection, which apart from giving label also give the location of that object. Let's say, okay, this is a traffic light, it creates a bounding box, this is a car, right? And all this. Then comes depth estimation. That is similar to what we have using stereo vision. You have two cameras which are placed side by side to each other, and using the stereo vision, similar to what we use in our eyes, we try to estimate depth of every pixel. And finally comes semantic segmentation, that is allotting a certain value to one type of object in an image, which we'll study a little more after some time, right? So feature extractors play a very vital role in that. You must have used many feature extractors like VGG, ResNet, Inception in while your course of learning machine learning and deep learning, right? And they are a very active area of research, and new extractors are coming at every moment, right? So we use convolutional neural nets for 2D object detection, where we create bounding boxes around a certain object, and various algorithms used include YOLO, efficient net, etc. Right? Then comes semantic segmentation. What is semantic segmentation? It gives a certain value, in this case, a certain color, to one kind of pixels in the image. Let's say it allots a purple color to all the pixels which are on road. It allocates a pink color to the footpath. It gives green color to the vegetation. It gives blue color to the, let's say, vehicles. So that is how computer gets to know what all is it in front of it. And currently there are different types of semantic segmentation architectures, including HRNet, deep lab, etc., which you can always search on Google and try to implement that. And this is one of the major thing where we are trying to decrease the computational expense. Currently semantic segmentation neural nets include like billions, 6 billion parameters. That is quite difficult to manage on nominal hardware which can be installed in a self-driving car. So making those computationally expensive is a great challenge for self-driving car industry. Then comes 3D drivable surface estimation, trying to know where the car can drive itself. How it is done: you generate a semantic segmentation output of a image. Let's say there is a certain frame from the camera, right? You choose 3D points on that image, you allocate 3D points on that image, and using that you create a drivable surface. And one of the most famous algorithms that we use to do that is a rank called Rensec algorithms, that uses three non-collinear points to estimate a 3D drivable surface, which in this case is a road. From your data, you randomly select 3 points. You compute model parameters using least square estimations. You count the number of inliners. If inliners is greater than a certain threshold value, you return the computed plane parameters to create a plane. Otherwise, go back to the step one until you get a 3D plane. Do search about this algorithm more on internet to actually know more, because there is a lot of mathematics that goes behind it. Then comes semantic lane estimation. For lane estimation, we use generally we use hot transform to detect lines in an output edge map. That is basically to detect the lane markings, all the boundaries of the road, so that computer can know which lane the car has to drive in and which not. Then comes hierarchical planner, which we use a tree-shaped approach to actually planning what all computer has to do to drive a car. Number one is mission planner. Where have you have to go? Let's say you have to go from Delhi to Bombay. That is mission planning. Then comes behavior planning. That is reacting to certain stimulus on the roads. Then comes local planner, which includes two things, that is path planner, determining the path, and velocity profile generator, which generates how much speed the car has to maintain so that it is a smooth drive for a traveler. And finally, the actual control in the vehicle. Mission planning, you already have seen examples in your Google Maps when you search for a certain location and try to find the shortest path to certain location. There are various types of algorithms used in graphs basically, which includes Dijkstra's A star, which try to find the shortest and the most efficient path in a graph, right? And then to improve the prediction of a vehicle, we use certain heuristics, what we call jugaad in certain, like in Indian accent. That can be, you can assume that vehicle in a certain driving lane will follow that lane. Okay, if a vehicle gives indicator, then there are chances that the vehicle will turn. Or even you can, to improve prediction, you can make use of various road signs, where okay, if there is a stop sign, then there are chances that the car in front of you will slow down its speed, etc. And then we use finite state machines. That is similar to what we have is if else statements, that is used in machine learning to know whether what to do next, right? If a speed of the car is above a certain threshold, it deaccelerates to stop, and then it checks these are basically if else statements. Then it checks again, and if that distance to stop sign decreases than certain threshold, you track speed and you increase it again. So yeah, you check the speed. If it's right, you maintain it there. If it's less, you either go up or down. And these are like a combination of if else statements only, right? So this is what is all basics go behind self-driving car. And it is not an easy task. Though I can't cover everything in detail in a lecture, this was a very basic intro, and currently the industry is at a greater power level, and many more researches have been done in this field. uh, MIT has been researching on these, and there is various companies like Comma AI, Waymo, a subsidiary of Google, Tesla, obviously, the grand Elon Musk vision, then Nvidia Drive, Uber, and yes, in India we have Minus Zero that is trying to achieve the similar thing. So this is what all goes into self-driving car, and uh, this is the very field of automotive industry where you need not to have to be an expert in only the mechanics of a car, but even the people in the deep learning scenario, deep learning field can actually venture out into this field in these various companies. So I hope you enjoyed this lecture. There are a lot of things that go behind, and due to very less duration of time of this lecture, I can't cover everything, but I hope that it sparks an interest of yours in this subject and you try to learn more about it in the future. So this is my LinkedIn ID. You can follow me there to stay updated on various advancements in this field and what all progress are is being done at companies like Minus Zero, Swath Robots, etc. in India also in this field of self-driving cars. Thank you, and I hope it was a great session.